Pilot 2.8 Aerodynamics of Flight. Let's shift our focus to the critical aspect of equipment use, autopilot systems. In a single pilot environment, an autopilot system becomes a valuable tool, significantly reducing workload. This allows the pilot to focus on other essential flight deck duties, enhancing situational awareness and minimizing the risk of controlled flight into terrain, CFIT, accidents. However, the challenge lies in assessing the impact of an inoperative autopilot. If known to be inoperative before departure, this information may factor into the evaluation of other risks. For instance, if a pilot plans a VOR approach on a dark night into an unfamiliar airport, relying on a functioning autopilot for a coupled approach, a malfunctioning autopilot could elevate the risk from medium to serious. In such cases, alternatives need to be considered. Conversely, if the autopilot fails during a critical, high-workload phase of the flight, the pilot must be prepared to take prompt action. Properly handling an autopilot failure is crucial, and pilots should study the issue before departure to determine response procedures well in advance. Now, let's delve into the critical aspect of pilot familiarity with aircraft systems. Here, discipline plays a pivotal role in ensuring success. If a pilot is unfamiliar with any aircraft systems, this will add to workload and may contribute to a loss of situational awareness. This level of proficiency is critical and should be looked upon as a requirement, not unlike carrying an adequate supply of fuel. So, let's not view unfamiliarity with the aircraft and its systems as a risk control measure, but instead as a hazard with high risk potential. Now, interestingly, what are they indicating? Chances are that the analog pilot will review the top display before the bottom display. Conversely, the digitally trained pilot will review the instrument panel on the bottom first. Now, shifting our focus to automation, it can be a valuable assistant, but its benefits hinge on a thorough understanding of the systems in use. This understanding fosters respect, which is achieved through discipline and mastering onboard systems. Pilots, now, should aim to fly the aircraft using minimal information from the primary flight display, PFD, encompassing turns, climbs, descents, and approaches. Reinforcing onboard suites involves leveraging computer-based software and incremental training to enhance pilot comfort with these systems. Now, regular practice is key to gaining experience and significantly reducing workload. To work effectively with automation, pilots must move beyond rote workmanship, avoiding a mechanical, sequential process. The goal, now, is to achieve competency and comprehend system operations without constant reliance on memorized sequences. This depth of understanding benefits pilots in diverse situations with increased tasks. Now, contrary to misconceptions, flight in aircraft equipped with different electronic management suites demands the same attention as analog-equipped aircraft. Pilots should familiarize themselves with the specific ways electronic flight displays, EFDs, are used in a particular aircraft. Now, two simple rules for EFD use include maintaining the ability to fly the aircraft to PTS standards and thoroughly understanding the electronic flight systems manuals, encompassing Autopilot and other management tools. Now, before mastering aircraft automation, pilots must have a solid foundation in flying the aircraft manually. This includes maneuvers training, as a substantial percentage of general aviation accidents occur during landing and takeoff. An identified safety issue relates to pilots developing an unwarranted over-reliance on avionics, expecting the equipment to compensate for their shortcomings. Advanced avionics pilots should focus on decision-making, and the Federal Aviation Administration study found that poor decision-making is a significant factor in accidents involving high-performance aircraft used for cross-country flight. Key flight management skills, information, automation, and risk, are crucial for safely navigating advanced avionics. Now, let's delve into the realm of information management when dealing with advanced avionics. For pilots making the transition to these systems, the wealth of information displayed on screens such as PFD, MFD, and GPS, VHF Navigator might seem overwhelming. It's akin to dealing with computers that store folders on a desktop and within a hierarchy. The first crucial skill in information management is grasping the system at a conceptual level. Understanding the organizational structure aids in navigating the available information. Memorizing knob and dial procedures is insufficient. A deeper understanding of how these systems work enhances procedural memory and equips pilots to handle unforeseen issues. However, recognizing the limits of understanding is equally important. Complex avionics systems have behaviors that may not be fully comprehended. Anticipating surprises and adopting a continuous learning approach proves more effective than attempting to memorize every knob manipulation. Utilizing simulation software and specific system-related books becomes invaluable. The second critical skill involves a practical approach: stop, look, and read. Instead of fixating on memorizing every sequence of button pushes, pulls, and turns, pilots are better off stopping, looking at the information available, and reading before manipulating controls. This approach can prevent potential issues. Once immersed in the display screens, the pilot's objective is to meter, manage, and prioritize the information flow to accomplish specific tasks. Flight instructors and pilots transitioning to advanced avionics can benefit from corralling the information flow. Configuring PFD and MFD screens based on personal preferences is one tactic, including options like north up, track up, DTK, desired track up, and heading up. Additionally, deciding how much information to display and tailoring it to suit the needs of a specific flight are effective strategies. Information flow can be further managed for specific operations. Pilots have the capability to prioritize information display for a timely presentation of exactly what is needed for a particular flight operation. For example, setting map scale for en route versus terminal area operation, using the terrain awareness page on the MFD for night or IMC flights in or near mountains, displaying nearest airports inset on the PFD during night or over inhospitable terrain, and programming the weather data link set to show echoes and METAR status flags. By employing these strategies, pilots can navigate the wealth of information provided by advanced avionics systems more effectively and enhance overall safety and efficiency. Now, let's delve into the significance of enhanced situational awareness in the context of advanced avionics. Despite explicit warnings in aircraft flight manuals against relying solely on certain displays, these tools offer pilots unprecedented information to improve their awareness of the situation. However, without a carefully planned strategy for managing information, there is a risk of pilots becoming overly dependent on these tools, adopting a passive role. Consider a pilot who solely follows the magenta line on the moving map. While convenient, this approach poses risks, such as flying into high terrain or prohibited airspace if the GPS course takes a straight line through such areas or if the moving map malfunctions. To maintain situational awareness and prevent overreliance on automation, it's crucial to implement effective information management strategies. Two fundamental procedures include double-checking the system and using verbal callouts. Verifying that the presented information makes sense is a minimum requirement. Callouts, even in single pilot operations, are valuable for situational awareness and information management. Here are additional practices to enhance and maintain situational awareness. Perform verification checks. Before departure, thoroughly check all information programmed into the system while on the ground. Check flight routing. Ensure that the programmed routing matches the planned flight route. Use a paper log to compare planned routes, headings, and leg lengths. If discrepancies arise, don't assume the computer data is correct. Double-check the entries. Verify waypoints. Confirm the accuracy of waypoints entered into the system. Utilize onboard navigation equipment. Use all available navigation tools on board, such as VOR, to complement and back up GPS, and vice versa. Match automated system use with proficiency. Stay within personal proficiency limits when using automated systems. Plan realistic flight routes. Consider potential airspace restrictions and rerouting possibilities, especially in situations where the onboard equipment suggests a direct flight but airspace considerations may require adjustments. Verify computer data entries. Be prepared to verify entries, especially during high workload periods, to avoid errors that could compromise situational awareness. By incorporating these practices into information management strategies, pilots can harness the benefits of advanced avionics while maintaining an active and aware role in command. Now, let's explore the crucial aspect of automation management in the context of advanced avionics. These systems provide a spectrum of automation levels, necessitating a pilot's adept management of the course deviation indicator, CDI, navigation source, and autopilot. Understanding the specific nuances of the automated system in use is paramount, ensuring anticipation of system behavior, vigilant monitoring, and swift corrective action if deviations occur. At a fundamental level, managing the autopilot entails constant awareness of engaged and armed modes. Verifying that armed functions, like navigation tracking or altitude capture, engage when expected is essential. Employing the callout technique post-arming, especially for course or altitude changes, enhances automation management. In advanced avionics, effective automation management extends to comprehending how the autopilot interacts with other systems. For instance, altering the navigation source on the ESHI may disengage the autopilot's nav mode in certain scenarios, necessitating prompt re-engagement to maintain desired navigation tracking. Now, let's shift our focus to risk management, the third crucial flight management skill. While enhanced situational awareness and automation capabilities amplify safety and utility, there's a potential risk of reduced vigilance due to lighter workloads. Humans tend to monitor automated systems poorly, particularly when the system is reliable, creating a paradox of automation. Although advanced avionics improve safety, they don't substitute basic flight knowledge and skills. The pilot must avoid over-reliance on gadgets and acknowledge the limits of electronic systems in GA aircraft. Risk escalates when the pilot fails to monitor systems actively, leading to detachment and a passive role. Complacency can have severe consequences, as demonstrated by a tragic 1999 accident in Colombia where pilots, equipped with proper charts and tools, allowed automation to navigate into a mountain due to inattention. This incident underscores the importance of continuous evaluation and risk management, as even self-induced hazards can arise from complacency. For GA pilots transitioning to automated systems, understanding the inherent risks in technical devices is crucial. Knowledge, experience, and adherence to mission requirements tilt the odds in favor of safe flights. Advanced avionics simplify tasks but demand proper training and operational equipment for their effective utilization. In summary, this discussion has centered on enhancing admiral skills to mitigate risk factors in both classic and automated aircraft. Ultimately, the focus is on the individuals who operate these aircraft, emphasizing the critical role of human decision-making and competence in aviation safety.